Hello guys, this is Jagannath Jadhav, and first of all, I would like to thank Prodigy Infotech for providing me with such a wonderful opportunity to explore myself in the domains of machine learning. So let's jump into the task one, which they have given to all their interns, is implement a linear regression model to predict the prices of houses based on their square footage and the number of bedrooms and bathrooms. So I've already opened the Kaggle dataset over here. We have 4 files. I downloaded it all and saved it into a folder, and then opened Jupyter Notebook inside that folder. So I have this notebook over here. So I'll just walk through this project one by one, that what kind of knowledge I gained by doing this project, and what kind of perspective has changed regarding the machine learning journey. So this is the first thing I have done is imported all the necessary libraries, uh, and then basically I just started working with the train.csv. So I created a data frame, train df. I pulled out train.csv inside it, and I just wanted to look what columns I have inside the data. So I just pulled out all the columns inside. Now the thing was, I was bothered about the square footage and number of bathrooms and number of bedrooms, uh, wale columns, like the columns which were responsible for the feature. But the thing was, there were many. So first of all, I just uh, created a filtered out data frame where I had only the columns which were numerical. So like we know that there are two types of columns, categorical ones and numerical ones. And I got to know that in the model we can feed inside categorical columns as a feature to train the model, but only numerical columns can be fed inside the model to train the model. So basically I just filtered out all the numerical columns and created a correlation matrix with respect to sale price. Now sale price is the price of the uh, property or real estate, and I arranged it in a descending order. So the number, if it's close to 1, like we can see that 0.79 is close to 1, that means it's highly correlated to sale price. And then as we go far away downwards, as we can see, there are negative correlated values also. But we can distinguish between highly correlated, like that means strong correlation, and weak correlation. So uh, the stronger the correlation, the better the model will predict. Okay, so uh, I got to know that okay, I have so many columns which are strongly correlated to sale price. But then I was like, okay, cool, I have a lot of columns. I was like, okay, I have a lot of columns to work with, but uh, what are the required columns? So I just created a list of all the required columns which were required to calculate the total number of bathrooms and total number of surface area, or else we can say that total number of square footage. So I figured out that there were 4 columns. Two were bothered about the number of bathrooms inside the basement, and two were about full bathroom and half bathroom. So I just summed it up and made a new column called total bathroom. Okay, and in the same way I calculated all the square footage, first floor square footage, second floor square footage, total basement square footage, and all the square footage uh, I needed to calculate. I just kept garage area aside from the total square footage. There was a reason for it, because garage area was holding, see, we can see garage area was holding a good correlation alone. That column was holding a good correlation. And also I was a bit of confused about the column, as in to add, if like should I add it in the square footage or not, because sometimes garages are counted inside the estate or the property, or sometimes they are they're not the part of the property. Like not all the real estate have a garage inside it. So it depends. So that's why I kept all the garage area column aside from the total square footage. So I got to got to know ki, okay, my two of the columns have been created, total bars and total SF. So this is the square footage, and these are the total number of bathrooms. Okay, so the thing is, after filtering out, after calculating the necessary columns, then too there were too many columns which were not necessary, because we have already calculated all these columns. we have already summed up them, so there was no need to show them again and again, because these are one and the same, uh, summed up into this column. So it's okay. I can just be bothered about the columns which are necessary for predicting the sale price. So now what I get over here of 6 column, उसमें से भी like out of that also I have sale price as the label, and all these five, these are called as the features. On the basis of features, the model will see all the patterns inside these features, the trends inside these features, and according to that it will predict a sale price. Okay, so I was cool about the concept. Whatever I was doing, I was not just blabbering about the data set. I was pretty sure that what I'm going to do after this. So now I have five features and one label. So I'm ready with the data to be fed inside the machine learning model. But before even feeding the data inside the model, there are some pre-processing to be done, which is called as pre-processing only. So I did some pre-processing. I split the data set into train set and test set. So basically, I split the data set in randomly such that the train set is 80% and test set is 20%. As you can see, the test size is 0.2, so it's 20%. So I I got two sets out of this data. Uh, Although I'd like to remind you guys that I'm still working with train.csv. I've not touched the final test, uh, test.csv. So I have split the train.csv into two data sets, that is train set and test set. So why did we do that? We'll figure it out later on as we go through the project. So, and after that, uh, I just split the data, the train set into two different things. That is, all the features and the labels. So I just dropped the sale price from the features, and in the labels I just kept the sale price. That's it. I didn't keep the features. Okay. So, and here I have created a pipeline. Basically, don't get too much into that. Pipeline is basically giving your data set a flow. Pipeline is giving a data set a flow that, when you send your data through that pipeline, some processes are happening, and after that, when the data comes out of the pipe, the data is processed. So it's basically that. So I did simple imputer. Simple imputer is basically replacing all the NaN values with the strategy I used, because here I have used median. So all the uh, actually, I was very fortunate that all these columns were not containing any null values or zeros. I'm not bothered about zeros, but null values and NaN values. There were no null values or NaN values, so uh, this process was not required. But still, I have kept it for my better understanding, that in case if I have some null values, that can be replaced by the median. The strategy is equal to median, is meant by all the null values are replaced by median. We can replace it by a mean also. It's totally on our understanding about the data. So later I scaled the data sets. I scaled the features basically. Why? Because square feet, or square footage, uh, is in different units, you know, and number of bathrooms is in different units. I mean, let's say an example, over here, where, yeah, over here, total square footage is in thousands, whereas total bathroom is in fours, like it's in single digits. So basically, it gets difficult for the machine to compare all the features. So bring it down to the same level of scaling. That is meant by standard scaling. So basically, I these numbers are now, like, as soon as I feed my data housing, that is all the features are fed into the pipeline. You can see that the X train is created, and these numbers are very different than these numbers, because they are scaled in a very you know equivalent format, where you can just feed these numbers inside the machine, and the machine will calculate all the, like, it is easier for the machine to predict the data set, because we have scaled it, because the range of numbers has been decreased and it has been scaled. So I have also created Y train as housing labels. That Y train has only the values of sale price, so it is just a label row. Uh, It is just a column with all the labels. Okay, now let's move on to the next part, which is correlations. Here, we can look all the, you know, scatter plots and histograms. Basically, this is a matrix with diagonal containing all the histogram. Histogram is uh, basically a histogram is over like it is it is by itself only. So some bins are created, and it is showing us the distribution of density of data inside it. And whereas scatter plot is showing us a trend. As some feature is increasing, the sale price is also increasing. Some features are not showing a trend, but they have a different kind of pattern. So we just got to know that this total SF was showing a linear regression over here. Then garage area was also showing a linear regression over here. Whereas uh, total bath was not showing any pattern, but it was showing uh, it was it was it was not showing a linear regression. But if you see, it is a linear regression, but only the patterns are very structured in a manner, not like these these two scatter plots. So I got to understand about the you know visuals. From the visuals, I got to understand that how the correlation is working with sale price. And better visual was this, because this is a heat map of all the correlated values. As we can see that overall quality was the highest correlated, and and as we go above uh, in the heat map, the correlation factor decreases. So we got to understand how correlation is working, how we have prepared our data set, train set, test set. Now we will do the same thing for the test.csv, but only the thing is we just have to one more thing to be noticed about is in the test.csv we have only the features, we don't have the sale price. So basically uh, this will be fed inside the machine, and the machine will calculate. Calculate is a very wrong thing to say, because the machine doesn't calculate, it predicts the sale price. So there is a difference between calculation and prediction, because calculation can be done by a calculator also, but what machine learning does cannot be done by a calculator. So after having all the features inside the data frame, I then fed the data frame throughout my pipeline. So again, we have X test, which is in this format. Now the journey has ended till here. Now starts the machine learning part. Until now, we were just processing the data sets. We were just doing some, finding out the correlations. We were just figuring out what kind of data is necessary, what kind of columns are necessary, and we were just preparing the data to be fed inside the model. Now is the part where we are going to feed the model inside the, we are going to feed the model with the data set. So basically, here I have three models: linear regression, decision tree regressor, and the random forest regressor. Each and every model works in a different way. uh, I have kept three models because to compare them with the best performance. And I found out that random forest regressor was performing better than these two. So I have created an outputs .txt. I'll show it to you later on. First, we'll see that I have imported the model over here. I've defined that model is equal to random forest regressor, and model.fit is equal to xtrain and ytrain. Now we are training the data with by providing it the features and the labels inside the data, inside the model. So basically the model will do its working, and it will learn all the predictions and stuff. Now we are going to train the we are going to train the model. We have already fit these two data sets. Now we are going to find out x underscore train. X train, say we'll find out predict. Okay, so basically we are doing is we are we have all the sale prices. We have all the sale prices in the train data set. Still we are finding out a predicted sale prices, and we'll compare both the sale prices. Okay, so our original sale prices was this, and our predicted sale prices was this. So basically here we can see I've predicted it, and I'll compare it with the see here 14,000, okay, 1 lakh 45,283, and I'll compare it with this 1,45,000. So it's quite close to each other. Here we can see it's 172053 and it is 178000. Okay, that is also like you can see the machine has learned to predict the sale price, but it is giving out values away from the original sale price. Yeah, so either it is giving lower than the actual sale price or higher than the actual sale price. So that higher or lower distance is called as error. So basically, we have figured out that our machine is predicting, but we have some errors. So to minimize these errors, we'll calculate mean squared error from the machine, like from the training prediction and the actual training which has been done on the model. So basically we'll figure out the mean squared error, and then we'll find out the root mean square error. We'll just take a easy function np dot square root. We'll feed train msc inside it, so we'll get msc and rmsc inside it. But I was amazed by this number because that was so big in size. Because uh, I thought that okay, sale prices are also big in size, as in the numbers are very big in size, so it's okay. I can get a big error, but still, I was not satisfied with the uh, model prediction. You know, it could be better. So what I did was I did cross validation after that. What is cross validation? Breaking your data set into let's say 10 different parts. Now the model will keep the first part for testing, and baki ka, like rest of the part it will train, and it will use the first part for testing. Now in the second case, it will put second part as the testing, and 1 3 4 5 6 7, all the 10 uh, parts of data sets it will train. So basically it is randomizing the train sets and giving out better test results. Because basically it is like giving your model some wide range of experience regarding the predictions. And here I have said 200, so that means I have broke my data sets into 200 different parts, and the model will cycle the training methods into 200 different experiences. So that means, if imagine if you're training a human, you are training a human and telling and giving that human 200 different experiences at the same time. It's not possible for a human, but machines can do that. So we can feed them with 200 different experiences at the same moment. So basically, after calculating all the RMSE scores and stuff, these are all the arrays of 200. These are all the 200 RMSE scores. After looking at the RMSE scores, I figured out that okay, but I can't keep all the 200 RMSE scores. So I just kept calculating the mean and standard deviation of the RMSE scores. So here I have the actual mean of all the RMSE and the standard deviation of the RMSEs. So basically, when I compare uh, when I compare all the outputs, I get first place पे we get random forest regressor, because the least mean it has of 29,000 something. Linear regression gave me 32,000 something, and decision tree gave me 38,000. So the mean, higher the mean, higher the error. Lower the mean, lower the error. So basically, random forest regressor was the winner, and hence I just pulled out the data set, test data set. I predicted the test data set and created a CSV file, and voila, I've submitted it on Kaggle, and that was my first time, first that was my first machine learning project. So I was very bothered about the ranking and stuff. And here we can see that 3620, not bad on our first try. So that's it. Uh, I also uploaded my project on GitHub, as Prodigy Infotech has instructed us to do. So you can find the GitHub link and the Jupyter Notebook links down below. So thank you so much.